আসসালামু আলাইকুম এভরিওয়ান। আশা করি সবাই অনেক ভালো আছেন এবং সুস্থ আছেন। আমরা আজকে আবার চলে এসেছি বার্কের অনেকদিন পর দারুণ একটি লাইভ সেশন নিয়ে। এবং আজকের লাইভ সেশনটি কিন্তু খুবই দারুণ একটি টপিকের উপর, যেটি রিসেন্টলি পুরো বিশ্বে তোলপাড় সৃষ্টি করেছে। এবং আমরা পুরো বিশ্ববাসী কিন্তু এই নিউজটির জন্য অপেক্ষা করছিলাম যে কবে এই নিউজটি আমরা শুনতে পাবো। তাহলে আজকে এই নিউজটি কি সেই বিষয়ে আমরা একটু প্রথমে শুনে নিব এবং আমাদের মেন্টর সম্পর্কে একটু জেনে নিব। আজকে আমরা কথা বলবো ঐতিহাসিক সেই টেলিস্কোপ, জেমস ওয়েব টেলিস্কোপ নিয়ে আজকে আমরা কথা বলবো। এবং আমাদের নতুন যে মহাশূন্য টেলিস্কোপ জেমস ওয়েব উৎক্ষেপণ করা হয়েছে সেই ব্যাপারে আরো বিস্তারিত আমাদের এই লাইভ সেশন থেকে আমরা জানবো। তার আগে আমরা একটু জেনে নিতে চাই যে আমরা কে কে এখন পর্যন্ত লাইভে জয়েন করেছি এবং কোথা থেকে জয়েন করেছি। যদি একটু কবে আমরা জায়গার নামগুলো উল্লেখ করে দিই তাহলে আমাদের আহ সুবিধা হয়। এবং ডেফিনেটলি তোমরা সবাই লাইভটি শেয়ার করে ফেলো সবার বন্ধুদের সাথে এবং সব জায়গায়, সো দ্যাট মোর পিপল ক্যান জয়েন ইন দিস লাইভ সেশন। এন্ড ইয়েস, আমাদের এই বর্তমান মহাকাশ গবেষণায় এক নতুন যুগের সূচনা কিন্তু ঘটিয়েছে বিশ্বের সবচেয়ে ক্ষমতাশীল একটি দূরবীক্ষণ যন্ত্র, যেটা মহাকাশে অলরেডি উৎক্ষেপণ করা হয়েছে। যার নাম আমরা সবাই জানি, জেমস ওয়েব স্পেস টেলিস্কোপ। তো জেমস ওয়েব স্পেস টেলিস্কোপ কিন্তু শনিবার 25শে ডিসেম্বর শনিবার গ্রিনিচ টাইম অনুযায়ী দুপুর 12টা 20 মিনিটের দিকে ফ্রান্সের গায়ানার যে কৌর মহাকাশ কেন্দ্র আছে সেখান থেকে যাত্রা শুরু করে। এবং ডেফিনেটলি ওই ইউরোপিয়ান এরিয়ান রকেট দিয়ে কিন্তু এটিকে উৎক্ষেপণ করা হয়। এবং নতুন এই টেলিস্কোপের কিন্তু পেছনে অনেক অনেক খাটাখাটনি রয়েছে, অসংখ্য বিজ্ঞানী, অসংখ্য ইঞ্জিনিয়ার কিন্তু কাজ করেছে। সো ডেফিনেটলি এই টেলিস্কোপটি কিন্তু অনেক ঐতিহাসিক একটি টেলিস্কোপ এবং অনেক গুরুত্বপূর্ণ একটি টেলিস্কোপ, যা আমাদের জন্য মহাকাশের অসংখ্য ঐতিহাসিক এবং রহস্যময় ইনফরমেশন আমাদের প্রদান করবে। সো এই বর্তমানে যে হাবল নামে যে মহাশূন্যে যে টেলিস্কোপটি কাজ করছে তার চেয়েও কিন্তু এটি প্রায় 3 গুণ বড় এবং 100 গুণ বেশি শক্তিশালী। এবং এটি নামকরণ কিন্তু করা হয়েছে যুক্তরাষ্ট্রের অ্যাপোলো চন্দ্র অভিযানের অন্যতম স্থপতির নামে। সো আমি আর দেরি করতে চাচ্ছি না, আমি আমাদের লাইভ সেশনটি আমাদের মেন্টরের কাছে হ্যান্ড ওভার করতে চাচ্ছি। সো আজকে আমাদের সাথে আমাদের লাইভ সেশনে আমাদের মেন্টর হিসেবে জয়েন হয়েছেন, আহ আপনারা সবাই দেখতে পাচ্ছেন, হয়তো এর আগেও আমরা দেখেছি, আহ, যাকে আমরা এর আগেও বিভিন্ন প্রোগ্রামেও পেয়েছি এবং বিভিন্ন রকমের ওয়েবিনারও আমরা কিন্তু তাকে এর আগেও আমরা এনেছি বার থেকে। এবং আমরা আবারও বেসিক্যালি তাকে এই মেন্টর হিসেবে এনেছি যেন আমরা তার কাছ থেকে আরো বেশি আরো ডিটেলস জেমস ওয়েব স্পেস সম্পর্কে জানতে পারি। সো বেসিক্যালি টুডে উই হ্যাভ আওয়ার ওন honorable guest and mentor, Dr. Martin. So, Dr. Martin, can you hear me?
Yes, I can hear you. Thank you, Rifat.
Hello. Okay. Yeah, how are you?
I'm very good. Very good at this time of year. I wish everybody a good holiday, and I hope everybody is COVID-free.
Okay, so let's get introduced at first. Yes.
Okay. So my name is Martin Braddock. I'm based in the United Kingdom. I'm a very keen astronomer. Work in the field professionally. I work in the field of drug discovery and drug development. And my talk today is on behalf of Sherwood Observatory, which is a private observatory based in England in the United Kingdom. And I'm really looking forward to telling you about the James Webb Space Telescope. Okay, so let me share. And please tell me that you can see the presentation. Okay, is that visible to everyone?
Yes, it's visible. Yeah.
Okay, so thank you very much. So thank you again for the kind invitation. And I've called this James Webb Space Telescope Shiva Borodin 2021 as a way of celebrating the great day that marked the launch of the James Webb Space Telescope on Christmas Day for those of us who celebrate Christmas on the 25th of December, just 3 days ago. And what I want to do, okay. Okay, and what I want to do is, first of all, give a little bit of an introduction as to who was James Webb and why is it called the James Webb Space Telescope? Why do we need it? What is the process now that it's been launched and the commissioning part of the James Webb Space Telescope? The components and instruments, its orbit at L2, and what does L2 mean? Its performance versus other telescopes, and the telescope's 4 science themes. What will it do, what can it do, and what might it do? And then to summarize for us. So why is it called the James Webb Space Telescope? Well, it's named after James Webb. And James Webb was NASA's second administrator in the 1960s. He was acknowledged as being an administrator, I think, rather than a scientist, but it's thanks to him that we have the success of the Apollo missions in the 1960s. And with anybody in that position, he has an organizational role that helps the scientists do the work that they do. And on the right-hand side here, part of the politics, of course, in the 1960s was to make sure that there was interest in the space program. And James Webb on the right-hand side here is pictured with Harry S. Truman, the United States president at the time, at the NASA headquarters in 1961. So some simple key facts. So it's actually known as the James Webb Space Telescope, but it was formerly known as the Next Generation Space Telescope and a successor for Hubble. It is an extraordinary machine. Its sun shield measures 21 by 14 meters. And for those of you who play tennis, that is about the size of a tennis court. Its launch mass is just over 6,000 kilos, 6,200 kilos. And its cost to build over $10 billion. And it's had many delays over the years, as I'm sure you know. Its original cost was around $1 billion, and the original blueprint is shown up in the top right-hand corner. And of course, it was launched at 12:20 on December the 25th. We expect to see first images within the next 2 to 3 months, and it's been a 30-year collaboration between NASA, the European Space Agency, and the Canadian Space Agency. It's likely having a mission duration of 5 to 10 years, and it will be orbiting at 1.5 million kilometers from Earth. And I'll mention a little bit about the Lagrange L2 point a little bit later. So the bottom right-hand panel is, I think, something that I'm sure you've seen many times before. It's one of the wonderful illustrations of the cosmological formation and development of the universe. And we're expecting the James Webb Space Telescope to see backwards to around 200 million years after the Big Bang. So again, I've put together some illustrations for you, and all of these are courtesy of NASA and the European Space Agency. You can see the scientists on the right-hand side and on the left-hand side at the bottom, and you can see this wonderful honeycomb mixture of hexagonal panels that form the mirror. And there are 18 of these panels altogether. That gives some appreciation, I think, of the sheer scale and size of the telescope itself. This shows a little bit about how the telescope has been packaged. So again, you can see the size of it in total. And I think of this a little bit like it's like packaging up an origami puzzle, if you've ever done it. And of course, the reason that it's packaged this way is that it has to be launched into space. And you can see this tilt to start off with. This is it in its upright position. And the panel on the right-hand side is it's gradually being moved in position to put onto the Ariane 5 rocket. So it's a terrifically complex piece of machinery. And I think when we come to look at its development over the years, we can understand perhaps just why it's taken so long to develop and what a fantastic technical achievement it has been just to develop it and get it into space. And of course, we greatly look forward to seeing the images it will produce. So it's designed this way, quite simply, to be able to fit into the nose cone of the Ariane rocket. So that, in a way, helps us understand why it is so intricately folded. And putting it inside this rocket, of course, is quite a delicate procedure, but nevertheless, it's been very successful so far. So I want to tell you a little bit now about what happens now it's been launched. To start off with, up in the top right-hand corner, the solar arrays will be deployed. We're going through that process right now. There's already been a first trajectory maneuver to start lining up the telescope with the orbit that it needs to go into. There'll be subsequently another trajectory maneuver and then communications of the antenna, the sun shield deployment, and I'll tell you a little bit about that in a moment too. And then first of all, the secondary mirror and then the primary mirror. And then lastly, there'll be a second trajectory maneuver, which is the major maneuver that gets it into place. So again, there is a complex set of procedures that need to happen, and they all need to happen correctly. There are 344 in total operating procedures that must work perfectly for the telescope to be in position and to be able to send images back. So again, for the coders amongst you, of course, this is all supported by Python code. I believe there are millions of lines of Python code that have all been tested, as you would expect, individually and in series and in parallel with other parts of the operations. All of these have to work perfectly for the telescope to give us what we hope will be its just returns. So I wanted to put just a little bit of detail here, and I'll summarize this in a diagram on the next slide. So we've now launched it, separated from the launch vehicle, deployed the high gain antenna. We're now waiting now for the second trajectory maneuver and the secondary mirror deployment. There's going to be a lag time between turning on the electronics, and that's because it's been shut down to protect the circuitry during the launch period. There'll then be a phase when the fine guidance sensor and the near infrared camera and spectrometer are turned on. There'll be some primary mirror segment adjustment and secondary mirror focus. So if you remember back to the picture that I showed you of the 18 panels, each of those 18 panels can work individually, and they all need to be aligned together to be able to give the mirror the true potential that it has to capture the light and to focus it onto the secondary mirror. That will happen over 3 months. Then there will then be some optimization of the near infrared camera, some further optimization of instruments, and it's expected that around about 6 months or 180 days, we'll begin to see the first science mission and to conduct the routine science operations, and more importantly, start getting back some pictures. So this is what it looks like in total. And again, all of these operations have to work perfectly, and they have to work at a point where they don't need human intervention, because unlike the Hubble Space Telescope that was in a relatively short orbit or in a relatively low orbit around the Earth, we won't be able to send astronauts out to fix any operating errors on the James Webb Space Telescope. So I thought it would be worth just telling you a little bit about Lagrange and Lagrange points, and apologies to everybody who is perhaps familiar with this, but it is I think, a fascinating scientific fact. So these were studied by Joseph Louis Lagrange, who lived in the 18th century. And at this point, it was thought impossible for anybody to be able to solve what's called the three-body problem, which is finding points where three bodies could orbit each other and stay in the same position relative to each other. And of course, this is complex mathematics. It's complex mathematics today. It certainly was in the 1800s. But at the Lagrange points, the gravitational pull of two large masses precisely equals the centripetal force required for a small object to move with them. And this is so important because without this, we wouldn't be able to maintain the orbit of the James Webb Space Telescope or anything else, as it would be affected by the gravitational pull, in this case of the Earth and of the Sun. And what Lagrange noticed is that there are 5 Lagrange points, L1, L2, and L3, and they all line up with each other, and L4 and L5 are at points of an equilateral triangle. And the James Webb Space Telescope is at L2, and I'll tell you why in a moment. So when we come to think about the Hubble Space Telescope, Hubble is orbiting the Earth around about 570 kilometers. Webb will orbit, as we've said, at around about 1.5 million kilometers, or 1 million miles, for those of us who work in miles still. And the reason that the Lagrange point is so important is because the telescope stays in line with the Earth as it moves around the Sun. This allows protection, especially with the deployment of a sun shield. If it didn't have the protection of the Earth, even with the sun shield that it has, it would be very difficult to be able to protect it in a way that would allow us to receive signals from deep space, which of course is the whole purpose of the mission. So I want to mention a little bit now about some of its components. And again, this is illustrated very nicely in a BBC Science Focus issue earlier this year. Mentioned already the secondary mirror, which is going to receive the light from the primary mirror. And the primary mirror, as you've seen, is composed of those 18 segments. And then there is the sun shield at the bottom, and it's this sun shield that is the size of the tennis court. The primary mirror itself is 6.5 meters, and I'll mention that a couple of times as we go. The second part of this is the, let me just go back if I can. So the secondary mirror reflects the light captured by the primary mirror and focuses it onto what's called an integrated science instrument module, or ISIM. And the reason that that's important is it's the ISIM that actually produces the images from the light captured by the secondary mirror. We have then what's called the spacecraft bus, which contains most of the steering and control machinery, star trackers, these wonderful little small telescopes that observe star patterns and help to aim the telescope. And then we have, of course, the part that's arguably the most important, which is the high gain antenna, because this transmits data back to Earth and it receives commands from NASA's Deep Space Network. And for those of you who remember the Mars talk that I gave to Bark earlier in the year, it's the Deep Space Network that is absolutely essential to be able to send signals back to Earth. So again, I put this in because I like the image, but I also like the fact that it shows that the orbit here is circular around this L2 point. So again, we have the Earth protecting the telescope from light and heat from the sun, or light from the sun, certainly at that distance. But of course, it's augmented by the heat shield, the light shield, the sun shield, and then we have this orbit around the L2 point. And what this gives us is it gives us a continuous viewing zone around the ecliptic pole here of around 5 degrees, and a continuous viewing pole away from the ecliptic pole of around 45 degrees with this 5% roll. And it's that freedom of movement, if you like, around the L2 point that should give us the possibility of getting some really, really first-class images. So what are its instruments? And again, just for reference, you can see that there is a person on the right-hand side here, one of NASA's scientists. There are a lot of abbreviations here. So NIRIS is a near-infrared imager and slitless spectrograph. MIRI is a mid-infrared instrument. NIRCam is a near-infrared camera, and NIRSPEC is a near-infrared spectrograph. So you'll notice here that the real intention here is to focus on capturing infrared light. And I'll explain as we go why capturing infrared light is more important, or is one of the most important aspects of the instrumentation. So this gives you, again, a little bit of an overview here of the four main instruments with their multiple modes. You can see near spec here, near cam, the nearest system, and MIRI. And again, it's the positioning of these instruments, how they will work in concert, that should allow us to build up some really, really detailed images capturing light in the infrared from galaxies and constellations formed just after the Big Bang. So I thought it would be worth capturing now just a little bit of detail on the light gathering power versus the spectral range when we compared the James Webb Space Telescope with the Hubble Space Telescope, of course, which we are very familiar with, and then perhaps the Spitzer Space Telescope, which perhaps we're a little less familiar with. And the most important part, I think, to understand here is that James Webb Space Telescope has a much, much larger light gathering capacity. It's around about 6-fold greater than the Hubble Space Telescope, and that will make a real difference. What James Webb does is it picks up where Hubble has left off. So it captures here a very broad wavelength range, perhaps not as short as Hubble, but this broad wavelength range here gives us, I think, a very happy medium between the Hubble and the Spitzer Space Telescope, acknowledging the fact that Spitzer's mirror is very small, tiny in comparison to the James Webb Space Telescope. So we have not just a broad wavelength of light collection, but we have a considerable light gathering capacity. And now when we come to think about the or the spectrophotometric performance, I think this is worth just taking a little look at, because James Webb Space Telescope here is at the bottom in red. You can see on both sides of the panel. Hubble is here. We have Spitzer, we have WISE, Sophia, Gemini, Herschel, and ALMA. And again, when we come to look at the photometric performance against a point source, so for the statisticians amongst you, you'll know that anything at a level of 4 sigma is likely to have 100% reality if the result has been generated. So to be able to measure and to be able to have certainty at 10 sigma in a 10,000 second integration means that any light that is captured during that integration has the spectrophotometric performance to guarantee that it is a real light giving event. Flux densities here are presented in Janskis. So for anybody not familiar with Janskis, a Jansky is 10 to the minus 26 watts per meter squared per hertz, which is an incredibly low amount of light, very, very low flux density. And again, when we look at the superiority of James Webb versus the other telescopes, we can see here that again, over a broad wavelength range, we are able to capture light way, way down in comparison to Hubble. So fantastic performance. And again, just think of all the scientists that have spent time on developing the optics for this telescope. It really is terrific. So there's just another point here that I wanted to mention, and I did smile a little bit because this is around resolution, and this is taken from the NASA website, but you can see that it's a little out of focus. So perhaps there needs to be a little more focusing within the NASA website. This is their diagram. And again, here we're looking at something here of low resolution, around about a resolution of 100, higher resolution here of 600 to 2400. These are point sources of light. This is spectroscopic measurements. And this is taken at a signal to noise range of 10, again in a 10,000 second integration, units expressed in Janskis. And again, you can see that for all of the James Webb instruments, they perform far better than the Hubble instruments, and certainly far better than the Spitzer instruments, both at low resolution and at high resolution. So we have something here that has terrific scientific performance in terms of what it should be able to capture and relay back to us. So just some other information here that again may interest you. So again, we're looking now at some instrumentation with telescopes that date back now to the 1980s and 1990s, including the Space Lab infrared telescope. Has quite a nice wavelength to be able to capture, but a tiny, tiny mirror, 0.15 meters. So again, when we come to look at what Hubble will bring, it will bring a good wavelength. Oops. Not sure what's happened there. It will bring a good wavelength of collection, but again, with a aperture mirror that far exceeds that from other space telescopes. So I said I'd mention a little bit now about the 4 science themes, and the 4 science themes are divided into really looking at first light and reionization, which is what happened after hydrogen and helium first formed as a consequence of the Big Bang. Assembly of galaxies on the top right, birth of stars and protoplanetary systems, and of course that's so essential for the production of the heavier elements that we know today, and something that's very close to my own heart that I'll spend some time on a little bit later, which is on planets and the origins of life. So I said I'd mention, why does infrared detection matter? And just remember again that the Webb telescope is really an infrared telescope. Well, it matters for 2 reasons. And it matters for the reason that I'm sure we're all familiar with, is that as a consequence of cosmic expansion, universe expansion, visible and UV light is stretched. And it's stretched, and of course, it reaches us as infrared light. So the detection of infrared light as we go back in time and as we go back in distance is absolutely essential, because if we can't detect infrared light that's been stretched as a consequence of universe expansion, we really are limited as to how far back we can see. So NearCam will take a series of pictures using filters. It will then use these changes in brightness to detect images, estimate the redshifts, which in turn will allow us to provide the distance. So that's the first reason why infrared detection matters. The second reason, and again, I guess we all know this, is that stars and planets that are just forming are hidden behind dust and absorb visible light. I think everybody recognizes that. And our longer wavelength, shorter frequency infrared radiation passes through, and that allows us to see what's behind. So if you like, we can imagine the Webb telescope as being a window into star and planet formation. And I've taken this image here, which I thought would interest you, of a galaxy here viewed in the visible and a galaxy here viewed in the infrared. And you can see that there is much greater quality of detail and much greater detail in general when viewed in the infrared. So again, another image here. This is of the Monkey Nebula in the constellation of Orion, and this is courtesy of ESA and NASA. And again, the image quality here in the visible, of course, these are false colors, so it looks very pretty, is nothing compared with the image quality when taken in the infrared. And again, these are both in wide field cameras, and you can see that we're starting to see now much more detail when the image is taken of the Monkey Nebula in the infrared versus the visible range. So what does it allow us to do? And what it allows us to do when we compare and contrast with the Hubble Space Telescope goods field, and I'll show you that in a moment, Chandra and deep field, is that it should allow us to get back to around about 200 million years after the Big Bang and after what we call the Dark Age, if you like, before atoms had started to come together. So we should be able to see some of the first stars And this will take us well back towards being able to understand what happened at the event of reionization, and what may have given rise to not just the first stars, but then starting to look at the first galaxy assemblies, which we're prevented by doing from Hubble simply because it doesn't have the same spectral range as the Webb telescope. So this is a little repetitive, but I think it's still worth making the point. 200 million years, if you don't remember anything else, just remember 200 million years post-Big Bang, when the first stars formed, and that's when we should be able to detect the light from them. We know, of course, that they're made of helium and hydrogen, and that supernovae were required to create the heavier elements that we detect in young stars today. And again, it goes without saying that infrared instrumentation is absolutely essential to be able to detect these very faint traces of light that have spent millions, if not billions of years to get to us today. So other science missions, and these are additional missions that I wanted to illustrate to you because I think these are just as interesting. And we mustn't forget that although the major reason for the Hubble Space Telescope is to have the understanding of basic cosmology, we've also got applications to understand dark matter and whether or not gravitational lensing can be applied to the most distant galaxies and start to understand the degree of galactic rotation. And again, if you think back to the work that Zwicky did in the earlier part of the last century, you'll know that it's thanks to him that we have an understanding of galactic rotation curves that suggests that we have dark matter in the universe, and that Hubble and particularly James Webb will be able to reaffirm that and detect it further. The gas giants, closer to home in our solar system, will be able to map atmospheric temperatures and determine chemical composition. Something, again, which is very close to my heart, which is an understanding of exoplanet atmospheres. And of course, with the discovery of the TRAPPIST-1 system 4 years ago now, there's been a lot of work conducted on understanding the TRAPPIST-1 system. James Webb Telescope will be able to help us now map the atmosphere composition to much more detail than we've been able to do previously, and perhaps start to answer the question, is it possible that these planets could host life? And then again, just for completion, I've put in here that there is interest for Pluto and the Kuiper Belt objects, really as a way of studying these bodies as almost leftovers from the early days of planet formation. So early target classes for Webb Telescope, there are 133 programs that have been earmarked for early release science that give what's called GTO. Again, there are a lot of abbreviations here, guaranteed time observation. And this is there purely to help reward scientists who developed a lot of the hardware and the software. And I think that's a fantastic enterprise to be able to allow the scientists to have, if you like, some guaranteed time observation. And then there will be general observer time that will be allocated through a proposal call that will be released next month. So again, anybody who's interested in getting time on the James Webb Telescope, there is a process to actually go through to get it. So some very famous targets that I think we all know and love. These will almost be used for practice. And we have the great observations, Origin Deep Survey, the good survey, up at the top left there, the Centaurus A galaxy, supernova SN 1987A, TRAPPIST-1b and 1e, and Neptune. So these will be almost practice to be able to really test out how good is James Webb versus our existing technology before we get into starting to test the real unknowns. So again, just put this in for completion. And the reason I put this in is I just wanted to show you the difference in operating temperatures. So the operating temperature for Hubble is around about 20 degrees Celsius. The operating temperature for James Webb is minus 230 degrees Celsius. So again, let's acknowledge, I think, and thank the scientists that have been able to develop the technology to allow instrumentation to work at such astonishingly low temperatures. And I put this in also because I love this. I'm a very visual person, so I like thinking in pictures. That's the Hubble primary mirror at the bottom. And that's James Webb up at the top. And it's around about six times the light gathering capacity. So this is the Hubble Space Telescope. And the reason I put this in is I just wanted to introduce you to something here that I find quite fun. So if you can imagine, this is me talking to my boss. And I say to my boss, I'd like to point the Hubble Space Telescope at an empty part of the sky for 10 days, please. I could be quite forgiven for my boss saying, are you crazy? But of course, for us who know the ultra deep field image, that's exactly what happened in 1995. 342 exposures, more than 100 hours. And it was pointed at an area that was as empty as possible. So we could see what Hubble would find beyond the stars of our own Milky Way and out past our nearby galaxies. And of course, we all know this very well. This is the Hubble ultra deep field image. This, I think, is probably one of the greatest images that we've seen collected in space. Can you imagine what that would look like? Actually, we probably can't imagine, but just imagine what that could look like when we have now applied the optics and the spectrometry and the photometric performance and the light gathering capacity of the James Webb telescope. I think we will look at this in the years to come and think this was the start, this was the baby step towards understanding what the images of the cosmos looks like. So one of the things that I said I was very interested in exoplanets and the possibilities of life elsewhere in the universe. And one of the questions that we're asking, of course, is could James Webb help solve the Fermi paradox? And for those of you who are not aware of Fermi, I'm sure most of you are. Enrico Fermi was an Italian and then naturalized American astrophysicist. And he simply asked the question, where are all the intelligent aliens? And the reason for him asking that is we know the age of the universe, we know the age of the sun, we know the age of the earth. There's been plenty of time for advanced terrestrial or advanced technical civilizations to be able to colonize the galaxy. And yet, as we all know, we are alone today, and there is no hint that we can even detect microbial life, let alone advanced life. So when we come to look at the number of exoplanets that we have so far, and these have been confirmed by tests, there are round about 4,500 confirmed planets and another 4,500 project candidates. So to me, it's only a matter of time before we will be able to have a short list of planets that we think could have the right properties to host life. And it's now thinking about, well, what can we do to make sure that we understand that a planet has an atmosphere that could maintain life? What biosignatures can we detect? And how could we use James Webb to be able to do that? So as a way of trying to understand this, I'm sure everybody is familiar with the Drake equation put forward in 1961. When you add them all up, what it comes to is around about 2,000 potential intelligent communicating civilizations that are in our galaxy. That is our galaxy alone. And of course, over the years, N has been revised downwards. And I've seen quotations of anywhere between 50, 100, 1,000, even 10,000. But whatever it is, if we don't actually look, we won't find. And of course, hence, that's one of the rationales for the search for extraterrestrial intelligence. But this, to me, is where James Webb can also play a role. And of course, if we assume that we have around about 10 to the 32 stars in the universe, n here, rather than being 2,000, could be 2 times 10 to the 35. So that is an extraordinary number. And even if that is a billion out, we still have an enormous possibility of perhaps being able to detect, when we can do it, intelligent communicating civilizations. So I mentioned a little bit about the TRAPPIST system, and in particular TRAPPIST-E and TRAPPIST-B. And these are 2 of the 7 exoplanets that orbit the TRAPPIST-1 star that have shown the greatest promise, perhaps, for having atmospheres that may support or may be indicative of being able to support life. And of course, the way that this is done is by simply looking at the stellar light and what atmosphere has been imprinted on the stellar light, and of course what that does to the spectrum of the light, which can then be related to the elemental composition. And there have been some very interesting publications over this last 12 months, one of which has been the characterization of the hydrospheres of the TRAPPIST planets, where it is shown that there is water, liquid water can be found. There may be a general increase with the semi-major axis, with the exception of planet D. And again, rather than go into the detail here, it tells us a little bit about why being able to measure the spectroscopic composition of the atmospheres on exoplanets is useful, because it's allowing us to put forward scientific hypotheses about what water may be located, where it's located, what the carbon dioxide content of the atmosphere may be, and then starts us to be able to hypothesize areas, building up an understanding of what biomarkers there may be on the surface of these exoplanets. And I think it's absolutely fascinating, and I can't wait to see what James Webb will do to add into this depths of science. So again, just as a little bit of a compilation here, there are many, many publications now on the TRAPPIST-1 system to be able to understand tidal heating and habitability, characterization of the atmospheres, intercomparison between the habitable atmospheres, and again, put forward in a specific workshop, and also to be able to look at the possibility of surface and oceanic habitability. Could you believe that this would have been possible just 10 years ago? And what might be possible now? We have James Webb, and hopefully once we have James Webb working correctly, we'll start to be able to understand the potential here of this system and other systems to support life. Well, I want to finish on something that was first put forward by Sarah Seeger. Sarah Seeger is an astrophysicist based at Massachusetts Institute of Technology. And in 2013, she came up with a very clever idea of modifying the Drake equation, and she called it the Seeger equation. And it was there specifically to estimate the probability of identifying an inhabited world within the next decade. So when she published this in 2013, that meant out to 2023. So we're not far off it. And rather than take the classical Drake equation, what she did is start to work through here the number of M-class stars, fraction of quiet stars, fraction within the habitability zone, fractions of transiting planets detectable by the James Webb Space Telescope, fraction with life, of course, pure speculation, and fraction with the detectable spectroscopic biosignature. And the answer comes down to about half. So what it's telling us is that it's very unlikely that we'll be able to detect an inhabited world, but at the same time, it's not impossible. And the reason, part of the reason why she put this together is that, of course, 10 years' time, that means something to us. We'll hopefully, we'll all be here in 10 years' time. So it is something to look forward to. If it was 100 years' time, it loses popular appeal to scientists, to even astronomers. It's a hard sell to be able to say, will probably detect life in 100 years' time, because none of us will be here. And I think why this is particularly interesting, and again, this is a little humorous, is that let's look on the bright side, because this doesn't include us. So there is the possibility, perhaps, that James Webb will certainly augment our search for biosignatures. And to me, along with our understanding of the early cosmos, they would be absolutely fantastic contributions to our scientific understanding, not only of how we've got to be here, but also are there other civilizations, perhaps advanced, perhaps not advanced, and is life widespread within the universe? So I want to finish up just with this last slide. So this, to me, makes our great day. This is a simple understanding that James Webb has a far greater sensitivity than previous observatories, much greater sophisticated instrumentation, including what's called integral field and multi-object spectroscopy. And again, just put down here in the bottom right, you can see the wavelength range and the flux density that can be measured with James Webb, far superior to the other telescopes. So I will finish here by saying that successfully launched on 25th of December at 12:20 UTC, launched in French Guiana at the Centre Spatial Guyanais in South America. And I hope I have this right here on the left-hand side here, but I loved this on the internet. Merry Christmas, NASA, we got you a new telescope as it's being launched. And then finally, on the page of science here, this was 5 years ago now, or nearly 6 years ago, February 2016, Eye on the Cosmos. And on the right-hand side, this is what we hope it will look like in 2 to 3 months when it's deployed and starts to send back signals. So thank you very much for inviting me. I hope you found that interesting, and I hope you learned something from it. I know there has been a lot of news, particularly in the last 3 days. So I'm sure you've seen this within your group, which is excellent, by the way. Really thank you for all the publicity that you're generating around supporting astronomy in Bangladesh, but also around the world. And I will stop there, and I'll be glad to answer any questions.
Okay, thank you so much for your amazing presentation. And যারা আমাদের অডিয়েন্স আছেন, তাদের যদি কোনো কোয়েশ্চেন থেকে থাকে, কাইন্ডলি আপনারা আমাদের কমেন্ট বক্সে জানিয়ে দিন। আমাদের মেন্টর আপনাদের কোয়েশ্চেনগুলো অ্যান্সার দিবেন, এবং আপনাদের যদি এই টপিক রিলেটেড আরো কিছু জানার আগ্রহ থেকে থাকে কিংবা রিসোর্সের প্রয়োজন হয়, সেগুলো আপনারা কমেন্টে জানাবেন, আমাদের মেন্টর সেগুলো রেসপন্স করবে। So yes, we are waiting for some amazing questions. Let's see how many questions we get so far. তোমাদের যা যা কোয়েশ্চেন আছে তারা কাইন্ডলি আমাদের কমেন্ট বক্সে একটু কোয়েশ্চেন গুলো করে রাখো, সো দ্যাট আমরা সেগুলো পিক করে আমাদের মেন্টর সেগুলো অ্যান্সার তোমাদেরকে জানাতে পারে। Okay, so Tahsin Islam is saying this was a very interesting live session. Thank you so much, Bart, for arranging this amazing live. Thank you for joining even, Tahsin. And I believe যে তোমরা আরো সামনে আমাদের সাথে কানেক্টেড থাকবে এবং আমাদের সামনে আরো দারুণ সব লাইভ গুলো তোমরা অংশগ্রহণ করবে, এবং তোমাদের জন্য একটা অ্যানাউন্সমেন্ট আসতে যাচ্ছে এই লাইভের শেষে। So stay tuned with whole live so that you can get that amazing announcement. Okay, so one question arrived from Sumaya Jahan. She's asking from where they did get this name James. You got the question?
Okay, so James Webb was named after the NASA administrator, not the first, but the second NASA administrator. And they chose him because he was really responsible for making sure NASA got the budget to support the Apollo missions. So James Webb, I believe, wasn't really a scientist. He was more an administrator and an organizer. And it's thanks to him that we have the Apollo program. And it's also thanks to him that we have I think a strong budget for space that NASA has today. And of course, like everything, it still has to fight for it, and it has to keep it. But it's in recognition of his support for the space program and for development of NASA space missions for Apollo.
Okay, great. I think Sumaya, you got your answer. Okay, so the next question from Ahnaf Siddiq. The question is, how long will the Webb mission last? Like about the James Webb Telescope, he's asking. How
So
will
it
it be long?
Yeah, so it should last 10 years. That's the aim. The Hubble mission should last 30 years. And of course, these will all work in concert. So Hubble isn't being turned off because James Webb is now launched. Hubble will continue to work and send back data. I think with most of these missions, these are the shortest lengths that we see them to be functioning. They will probably work for much longer than the 10-year period. So, but I would take it that James Webb will be operational for 10 years and possibly longer.
Okay, so we got another amazing question from Siddiq Rangpur. Why is the mirror gold quoted, and how much gold is used?
Oh gosh. Now I'm not sure how much gold is used, but it's not insignificant. And the reason that it's not insignificant, of course, is that it acts as an excellent insulator. It's inert, as I think we all know. So it's not going to be subject to any elemental corrosion. But the reason it's used, of course, is because it's super reflective. So it has the ability to be able to capture and reflect light, chemically inert. I think it is about 2 kilos that was used for the entire telescope. I think that's correct, but I'm not sure completely. But those are the main reasons that it's used, and of course that's what gives it its fantastic spectral power.
Okay, thank you for your amazing answer. So the next question from Astria. Will Webb be able to tell us more about the Big Bang?
Yeah, it should certainly be able to tell us more about the Big Bang. I think it will tell us a lot about what we call the reionization event. And in particular, that's so important because everything at the moment is still very theoretical. To be able to understand how hydrogen and helium have come together to make the heavier elements and ultimately fuse to be able to form suns that we know today isn't just of interest for an understanding of galactic and cosmic evolution. It's possibly interesting for our understanding of the basic mechanisms of nuclear fusion. And that, of course, has applications on Earth, perhaps, as a power source for the future. So I think there are many, many instances of where James Webb and other space telescopes can tell us not just about cosmic science and space science, but may have applications for systems on Earth that human beings will need in future.
Okay, thank you. And I think we have done for all the questions, and the time is over. So thank you so much, Dr. Martin, for your amazing session and your precious time. And I think we will get back to you soon in the next live session in future, hopefully, maybe in January, right?
Sure.
So thank you so much for your time, and thanks for your presentation.
You're very welcome. Thank you, everybody.
Okay, take care.
Bye.
Well, so তোমরা যারা আজকে লাইভ সেশনটি করলে, আমাদের 2022 সালে তোমাদের জন্য কিন্তু আমাদের পুরো টিম খুব দারুণ একটি কন্টেন্ট তৈরি করতে যাচ্ছে, খুব দারুণ কিছু সিরিজ নিয়ে আসতে যাচ্ছে, খুব দারুণ সব লাইভ ক্লাসেস নিয়ে আসতে যাচ্ছে। সো ইয়েস, তোমরা যারা বেসিক অ্যাস্ট্রোনমি শিখতে চাও এবং তার সাথে সাথে কিছু অ্যাডভান্সড শিখতে চাও, অ্যাস্ট্রোনমি, ম্যাথমেটিক্স দেখতে চাও, তোমাদের জন্য দারুণ সব কন্টেন্ট কিন্তু আসতে যাচ্ছে। এন্ড ডেফিনেটলি তোমরা বার্কের প্রত্যেকটি পেজের সাথে বার্কের ইউটিউব সাবস্ক্রাইব করে রাখো, বার্কের পেজের সাথে যুক্ত থাকো এবং আমাদের অফিসিয়াল গ্রুপের সাথে যুক্ত থাকো, যেন তোমরা লাইভ ক্লাসগুলো শেয়ার করতে পারো সবার সাথে এবং তোমরা নিজেরাও সেই লাইভ ক্লাস থেকে নিজেরাও কিছু শিখতে পারো। সো দেখা হচ্ছে পরবর্তী কোনো লাইভ সেশনে। ততক্ষণ পর্যন্ত সবাই ভালো থাকো, সুস্থ থাকো এবং সেফ থাকো এন্ড বাসায় থাকো। এন্ড বছরের শেষ সময়টুকু কে কিভাবে এনজয় করছো সেটা ডেফিনেটলি কমেন্টে জানিয়ে দাও, যেন আমরাও বুঝতে পারি যে তোমরা কে কতটুকু কত স্কিল গ্যাদার করতে পারলে। দেখা হচ্ছে পরবর্তী লাইভ সেশনে। আল্লাহ হাফেজ, আসসালামু আলাইকুম।